Every second, billions of data points race across fiber optic networks, connecting scattered server nodes to process complex requests instantly. This invisible infrastructure allows local devices to harness massive global computing power. Success in the Module 5 cloud computing exam relies on high-yield engineering intuition, moving past the limitations of memorizing definitions. We will achieve this by deconstructing the 3 core layers of your syllabus: the foundational AWS infrastructure, the Google App Engine platform lifecycle, and applied architectures mapping healthcare and media streaming. This diagram shows the universal system flow model you can apply to any exam question. Notice how it tracks from the data input, routes directly into a central cloud scaling engine, and finally pushes into an actionable output. By understanding this core abstraction, how physical hardware is converted into scalable digital services, you can derive the answer to any complex architectural scenario from first principles. This diagram maps the Amazon Web Services ecosystem into 4 distinct taxonomic pillars. AWS provides infrastructure as a service, which requires you to construct the precise environment your application needs. The compute pillar acts as the system's engine. It houses EC2 instances for virtual processing, Amazon machine images as templates, and auto-scaling to handle spikes. The storage pillar represents your data layer. Amazon S3 handles object storage using buckets, EBS provides persistent block storage, and RDS manages relational databases like MySQL. Next is networking, the nervous system. SQS and SNS manage messaging, Route 53 directs DNS traffic, and elastic load balancing distributes requests across multiple instances. Finally, the complementary pillar tracks system health. CloudWatch monitors CPU and network utilization, generating logs and alerts, while DevPay manages billing. Providing granular control over these building blocks requires the engineer to actively architect, manage, and secure every single component in the stack. While AWS provides the raw blocks, Google App Engine provides a fully managed environment. GAE is a platform-as-a-service environment where developers focus purely on application code, while Google manages the operating systems, networking, and scaling. This flowchart tracks the precise path of an incoming user request on Google App Engine. A user request hits the Google front end, where a load balancer distributes the traffic across multiple active runtime environment instances. To retrieve data, the runtime instance first queries Memcache. By temporarily caching frequently accessed data in memory, the system reduces latency. If the information isn't there, the request routes down to the distributed NoSQL Datastore. Applications also need to offload heavy background processes, like image conversion or email sending. Task queues execute these long-running jobs asynchronously, while the URL fetch service allows the app to communicate with external APIs. Before this architecture goes live, the application lifecycle begins locally. Developers write code, map URLs and configuration files, and test on a local server. Once deployed, the application executes inside a secure, isolated sandbox environment. This split-screen graphic illustrates the strict pay-per-use cost model in GAE. When user traffic hits a sudden spike, the platform automatically allocates new instances. On the right, the billing meter immediately ticks upward, driven by CPU running hours and network bandwidth. Reading, writing, and deleting records in the NoSQL Datastore is a major cost factor. Frequent database queries will rapidly inflate operational expenses. Optimizing these queries and utilizing Memcache are critical for maintaining cost efficiency. A PaaS framework trades low-level architectural control for increased developmental speed, automated fault tolerance, and absolute alignment between traffic and operational costs. This diagram outlines a direct comparison of 2 essential cloud characteristics: scalability and elasticity. On the left side, we see scalability in action. Scalability measures the overall capacity of a system to increase its hardware resources to meet demand. You scale vertically by adding CPU to an existing machine, and horizontally by adding new servers to distribute the workload. On the right, elasticity handles the dynamic provisioning and release of resources, strictly matching the real-time workload curve. Server instances automatically launch to absorb a sudden traffic spike and vanish the exact moment demand drops. Despite these automated features, developers must manage specific operational challenges: protecting user data from cyber attacks, mitigating network latency, and preventing vendor lock-in all require intentional architectural planning. Ultimately, elasticity is the mechanism driving the pay-per-use billing model. It ensures infrastructure scales so precisely that you never pay for an idle server. This architectural flow illustrates how cloud primitives assemble into a healthcare ECG monitor. The system starts at the edge with the patient ECG sensor and flows into the cloud processing layer. Continuous biometric data transmits from the edge sensor, hits the cloud storage, and is analyzed in real time by PaaS instances. If an abnormality is detected, the runtime instantly pushes CKSCS architecture used in bioinformatics. Predicting protein structures and classifying cancer genes demands enormous computational power. Massive gene datasets are fed directly into the Anika middleware orchestrator. The Anika middleware acts as the system's brain. It slices massive genetic datasets into pieces and distributes them across parallel cloud nodes. These nodes execute the data simultaneously, drastically cutting total computation time. This diagram details the underlying architecture for media streaming. To deliver heavy video files globally with zero latency, the data flows from cloud storage through streaming servers and out to the content delivery network. The content delivery network acts as a geographic edge cache. Instead of millions of concurrent requests crashing the primary streaming servers, users pull the video files from CDN nodes geographically closer to their devices. Cloud-based online gaming utilizes this exact same streaming pipeline, but adds a critical processing layer. By allocating virtual GPUs within the cloud, the system can compute heavy, real-time rendering and deliver interactive gameplay directly to user screens. Whether analyzing a heartbeat, predicting a protein structure, or distributing a live broadcast, the underlying mechanics of scalable distributed cloud infrastructure remain identical. Let's lock in these core system models for your final exam review. When analyzing AWS, categorize your answers into compute, storage, and networking. Use EC2 for raw compute processing, S3 for distributed object storage, and VPC for network isolation. For Google App Engine, define it firmly as a platform as a service. Highlight the automated sandbox runtime environment, the latency-reducing Memcache, and the strict pay-per-use cost model dictated by CPU hours and database operations. If you are asked to map a specific application architecture, rely on the universal drawing strategy. Sketch the flow originating at the edge sensors or user devices, route it through the cloud load balancers and compute nodes, and terminate at the actionable output. By mastering how these foundational architectures route, scale, and process massive datasets, you possess the engineering intuition required to confidently ace Module 5.